Good morning. I am Dr. R. Murali, Professor, Department of Mathematics, Dr. Ambedkar Institute of Technology, Bengaluru. I am delivering lectures in partial differential equations, which is module 3 in Engineering Mathematics 2 with subject code 15MAT21. In the previous sessions, we have discussed the following topics related to partial differential equations. We have seen how to form a PDE. Now, when we form the PDE, we have seen that Z is the dependent variable, which is dependent on the variables x and y. That is, Z is equal to Z of x comma y. Then we have seen that any differential equation which contains the partial derivatives of z with respect to x and y, may be first order, second order, or even higher, becomes a PDE. We have seen the numerous derivatives of z, dou z by dou x, dou z by dou y. Then the second order derivatives, dou square z by dou x square, dou square z by dou x dou y, and dou square z by dou y square. An equation involving such partial derivatives was classified as a partial differential equation. Then in the sessions, we have seen how to form a PDE. Given a relation, how to exactly form a PDE. We have seen that the formation can be done by the elimination of arbitrary constants and relations, and functions in a given relation. So, given an expression which contains constants as well as functions, you can obtain the PDE by eliminating either the constants or the functions in the relation. We have seen many examples based on that. Next, we have obtained the solutions of non-homogeneous PDEs by direct integration. We have seen that if z is the dependent variable dependent on x and y, if the PDE contains only the variable z or its partial derivatives, I repeat again, if the PDE contains z or its partial derivatives, such equations were called homogeneous partial differential equations. Now, equations that do not satisfy these conditions become non-homogeneous. We have seen the solution of non-homogeneous partial differential equations by a direct integration procedure. We have solved problems with conditions and without conditions. Next, in the previous session, we have looked into the solution of homogeneous PDEs, that is, PDEs containing the dependent variable z and its partial derivatives, involving derivatives with respect to one independent variable only. Either z will have the derivative with respect to x or the derivative with respect to y. Now, in today's session, we will look into some applications of PDE. One of them is the PDE called the wave equation, which has got lot of applications in vibrations of a stretched string, and the heat equation. So, we will be solving such equations in our next session using the method of separation of variable technique. But today, we will concentrate on the derivation of the one dimensional heat and wave equations. As you know, friends, partial derivatives have the added advantage that you can pick the variable and differentiate. For example, as you see here, z is a function of x and y, but you can define z as a function of any number of variables. So, if you want to vary only one of the variables in z, you can go for a partial differentiation. So, you can relax in the sense that you can differentiate according to the variable that is required in the problem. So, partial differential equations is one of the most fundamental areas in applied analysis, and it is hard to imagine any area of science and engineering where the impact of this subject is not felt. If you go to mechanical, you have partial derivatives, you go to civil, you have partial derivatives, go to electronics, electrical, any branch of engineering or in science, in some way or the other has partial derivatives and equations involving them. So, a number of problems in science and engineering, like the vibration of strings, that is what I told you friends, is related to the wave equation. Heat conduction, this is where you have the heat equation, and electrostatics will lead us to partial derivatives and equations involving them, namely partial differential equations, in short written as PDEs. Now, as you have seen friends in our previous sessions, we have solved two types of PDEs, one where the PDEs were non-homogeneous. In such equations, we have used a set of conditions. Also in homogeneous PDEs, we have used a set of conditions to determine the functions that are assumed in the solution. So, in physical problems, we seek a solution of the differential equation which satisfies some specified conditions called the boundary conditions. So, the differential equations together with these boundary conditions constitute what is known as a boundary value problem, or simply written as BVP. So, in today's session, we concentrate on the derivation of the wave and the heat equation. Let us go to the first derivation, which deals with the vibrations of a stretched string, which will result in a second order PDE called the wave equation. So, these are the assumptions. Observe the diagram. You consider a tightly stretched elastic string having length equal to L, then having fixed ends A and B, you can see A and B here. So, we consider the string to be placed on the xy plane for convenience. Now, this string is subjected to a constant tension T. So, it is quite obvious that if you have a stretched string like this, if you pull the string and release it, what happens? Obviously, vibrations occur. So, the wave equation will deal with vibrations of such strings. So, our assumptions we will repeat again. The string is of length L. Second, it has fixed ends A and B. So, you are securing the string at 2 points A and B, which is on the x axis, and it is subjected to a constant tension capital T. Now, what are the other conditions? The tension capital T will be considered large as compared to the weight of the string, so that the effects of gravity become negligible. So, initially take the string which is fixed at AB, let the string be released from rest and allowed to vibrate. So, you are starting a sequence of vibrations of the string. So, what are we going to do here? We study the subsequent motion of the string with no external forces acting on it. Second, we assume that each point of the string makes small vibrations at right angles to the equilibrium position AB of the string entirely in one plane. This assumption is very important. Let us move further, which will lead us to the derivation. Some more conditions. We consider capital A as the origin. We consider AB as the x axis. This is the x axis. Let me remind you friends that the string is fixed at the end points A and B. The motion of the string takes place in the xy plane. So, this is how the vibrations occur. You can see that the figure shows the string in the position APB. This is P, A, P, B at some time small t. Now, consider the motion. So, you are taking a small segment of the string and you are analyzing the motion of this element PQ. So, consider a small element PQ. So, you can see that PQ is here, small element PQ of the string between the points P x comma y, this is P. So, coordinates of P are x y and Q, which is a neighboring point to P as x plus delta x comma y plus delta y. That is to say, Q is at an incremental distance from P such that x changes to x plus delta x and y changes to y plus delta y, or equivalently it is a position very near to the point P. Now, the tangents at P and Q make angles of psi and psi plus delta psi with the x axis respectively, that you can notice here. This is angle psi, this is the tangent, right. So, it makes angle psi at P. So, this you have psi and it makes an angle psi plus delta psi. So, once vibration starts, obviously you have the component of the velocity and acceleration. So, since you are taking this in the xy plane, right, and you are assuming that the vibrations are along the xy plane. So, when you pull the string and leave it, these vibrations induce a velocity as well as an acceleration component, and with reference to time, because you are pulling it in the direction of the y axis, the element will be moving upwards with acceleration dou square y by dou t square. You know that friends, the second order derivative is nothing but the acceleration. Now, with these conditions, let us calculate the vertical component of the force acting on this element, and the vertical component of the force with a tension capital T, if you see the diagram, is capital T into sine of psi plus delta psi. You have this capital T sine psi plus delta psi minus capital T into sine psi. You have a common factor capital T in that. If you remove that outside, take T out, you are left with sine psi plus delta psi minus sine psi. But since psi is very small, because the element PQ is also very small and Q is at an incremental distance from capital P, sine psi plus delta psi and sine psi respectively can be equated to tan psi plus delta psi minus tan psi respectively. So, the expression capital T equal to sine of psi plus delta psi minus psi takes the form capital T into tan psi plus delta psi minus tan of psi. But you know that the geometrical meaning of tan is the slope, and slope is dy by dx in terms of the total derivative. So, because you are taking the vibrations in the xy plane, the equivalent partial derivative for the slope should be delta y by delta x. Hence, tan of psi plus delta psi, which is tan of this angle, should be the derivative corresponding to the point Q, where x is x plus delta x and y is y plus delta y, and tan of psi, which is the angle here. You can see psi here, this is psi plus delta psi, this is the angle psi plus delta psi, and this is the angle psi. So, the tan of the angle psi is related to the point P with coordinates x comma y. The tan of the angle psi plus delta psi is related to the point Q with coordinates x plus delta x and y plus delta y, and hence tan of psi plus delta psi can be approximated to the partial derivative dou y by dou x at x plus delta x. You can see that here, friends, delta y by delta x at x plus delta x minus delta y by delta x at the point x. That is to say, this derivative, which is the slope, is approximated at q minus the derivative approximated at the point P. Now, to go further, if you assume that small m is the mass per unit length of the string, then by Newton's second law of motion, you have mass into acceleration is equal to force. The force component is already calculated here, which is capital T dou y by dou x at x plus delta x minus dou y by dou x at x. That is substituted in the RHS in place of the force, and since m is the mass per unit length of the string, you have the mass component as m into delta x into acceleration, as we have seen in our previous slide, is dou square y by dou t square. The element moves with acceleration dou square y by dou t square. We have the relation m delta x into dou square y by dou t square is equal to capital T into dou y by dou x at x plus delta x minus dou y by dou x at x, or shift this RHS term m delta x to RHS. So, you get dou square y by dou t square equal to capital T by m into dou y by dou x at x plus delta x minus dou y by dou x at x whole divided by delta x. Now, before we go to the next step, let us come back to the figure. Now, q is an incremental point, that is to say, q is a point very close to capital P. So, to get back where the vibrations start, you take P, you consider the point P back to q back to P, that is, since q is at an incremental distance from the point P, taking the limits as q tends to P, as q comes nearer to P, you get the point P itself. Correspondingly, we have delta x tending to 0. So, what happens, friends? The left hand side dou square y by dou t square remains the same, but in the RHS observe that as delta x tends to 0, dou y by dou x at x plus delta x minus dou y by dou x at x by delta x goes to the partial derivative dou square y by dou x square. That is the definition of the second order derivative. So that you end up with dou square y by dou t square equal to t by m into dou square y by dou x square for all values of x from 0 to L, that is, you know that the length of the string is L, and for all time t greater than 0. Now, denoting c square as t by m, we have the partial differential equation dou square y by dou t square equal to c square into dou square y by dou x square. This is the partial differential equation giving the transverse vibrations of a string. It is also called the one dimensional wave equation. Now, in some of the notations, the variable y is also written as u, so that equivalently you can write dou square u by dou t square equal to c square into dou square y by dou x square, sorry, dou square u by dou x square. The physical constant capital T by m is denoted by c square because it indicates that this constant is positive, a fact that will be essential to the form of the solutions. We will see in our future sessions that when we solve the equation, we try to obtain various possible solutions of the wave equation. Also, one dimensional means that the equation involves one space variable small x. So, this is the derivation of the wave equation. Now, let us proceed to the derivation of one more important partial differential equation known as the heat equation. It is the one dimensional heat flow or the heat equation. So, what are the conditions? The first condition is you consider a homogeneous bar of uniform cross section alpha centimeter square. Condition 1. The sides of the bar are covered with a material impervious to heat, so that the streamlines of heat flow are all parallel and perpendicular to the area alpha. Next, one end of the bar is taken as the origin. So, this is, you can see O here, one end of the bar is the origin. The direction of the heat flow is taken as the positive x axis, that you can see written here. This is the direction of the heat flow. Assume that rho is the density, S is the specific heat, and K as the thermal conductivity, and let u x comma t be the temperature at a distance x. You can see that here. Let u x comma t be the temperature at a distance x from the origin O. Now, if delta u is the change in temperature in a slab of thickness delta x, I should show you the diagram again. The thickness of the slab is delta x. So, if delta U be the change in temperature in a slab of thickness delta x of the bar, then from the fundamental principles of heat conduction, we know that heat flows from a higher temperature to a lower temperature, and also that the quantity of heat in a body is proportional to its mass and temperature. We will use these properties, but the quantity of heat in the slab is S rho alpha into delta x into delta U. This expression can be arrived at immediately because of the fact that you have assumed that rho is the density of the bar, S is the specific heat, and K is the thermal conductivity. So, since delta U is the change in temperature in a slab of thickness delta x, the quantity of heat in the slab should be S into rho into alpha into delta x into delta U. Hence, we will apply this result now, which says that from the fundamental principles of heat conduction, the quantity of heat in a body is proportional to its mass and temperature. Hence, what should happen? The rate of increase of heat in the slab, which is as we see here, because as it varies with time, right, as it varies with time, the component delta U, incremental component delta U changes to delta U by delta T with time. So, S rho alpha delta x dou U by dou T, which is the rate of increase of heat in the slab, is equal to R1 minus R2, where R1 and R2 are respectively the rate of inflow and outflow of heat. To make this more clear, let us go to our diagram again. See the diagram. R1 is here. R1 is the rate of inflow of heat. Heat conduction happens in this direction from the origin towards the x axis, which is marked here. So, rate of inflow is R1 and rate of outflow is R2. Now, therefore, the rate of increase of heat in this slab, which is S into rho into S rho into alpha into this is rho, S rho alpha delta x dou U by dou T can be equated to R1 minus R2, where R1 and R2 are respectively the rate of inflow and outflow of heat. Again, from the fundamental principles of heat conduction, we have the property, the rate of heat flow across an area is proportional to the area, first proportional to the area and to the rate of change of temperature with respect to its distance normal to the area. So, two components here. Let me repeat again. The rate of heat flow across an area is proportional to the area first. You assume that area of cross section is alpha, and to the rate of change of temperature with respect to its distance normal to the area. So, the rate of inflow R1 can be written as minus K alpha into dou U by dou x corresponding to x, and R2 can be written as minus K into alpha into dou U by dou x corresponding to x plus delta x. the negative sign appearing due to the fact that heat flows from a higher temperature to a lower temperature. So that when you substitute these expressions in equation 1 here, S rho delta x dou u by dou t equal to R1 minus R2, you get S rho dou u delta x dou u by dou t equal to R1 minus R2 becomes, left hand side is unchanged, S rho alpha delta x dou u by dou t equal to, first we substitute R1 minus k alpha dou u by dou x at x plus k alpha dou u by dou x at x plus delta x, or take common factor k in this and write it in the reverse order. So, you get k alpha, k and alpha are constants, dou u by dou x at x plus delta x minus, this is the common factor, this k will not come here. So, it is k alpha dou u by dou x at, so what we do here, take this k and alpha common and write it in reverse order. So, you have k alpha dou u by dou x at x plus delta x minus dou u by dou x at x, or dou u by dou t, shift this sp alpha, s rho alpha and delta x to the denominator, you get dou u by dou t equal to k by s rho into dou u by dou x at x plus delta x minus dou u by dou x at x divided by delta x. Now, as you take the limit delta x tending to 0, as was explained in our previous derivation, this expression here tends to, these k values are absent, they are the common factors removed. So, this expression here tends to the second order partial derivative dou square u by dou x square. So, that you end up with the equation dou u by dou t equal to k by s into rho into dou square u by dou x square. So, that finally writing k by s rho equal to c square, called the diffusivity of the substance, we get dou u by dou t equal to c square into dou square u by dou x square, which is called the one dimensional heat flow equation. So, you have seen the derivation of two equations today. One was the one dimensional wave equation, which was dou square y by dou t square equal to c square into dou square u by dou t square, and the second equation was the heat equation dou u by dou t equal to c square into this dou square u by dou x square. Now, the next stage is to solve these equations, and to solve these equations we use a method called the method of separation of variables. Now, we will just give a brief introduction of the method of separation of variables. Now, let me remind you again, the wave equation was derived as dou square y by dou t square equal to c square into dou square y by dou x square. In this equation, observe that y is the dependent variable which is dependent on x and t. Y depends on x and t. And now, you have derived the heat equation, which is dou u by dou t equal to c square dou square u by dou x square. In this heat equation, u is the dependent variable dependent on x and t, and To solve these equations, we use a method called the separation of variables. I will briefly give you an introduction of this method. We will solve these equations in our next session. So, because x and t are the independent variables in both, you initially assume that, suppose I have u as a function of x and t, initially assume that the solution to the equation is of the form u equal to capital X into capital T, where capital X is a function of x and capital T is a function of small t. I am giving you this method with the understanding that u is dependent on small x and small t. So, start the solution by assuming the solution to be in the form u equal to capital X into capital T, where capital X is a function of x and capital T is a function of small t. Next, since u equal to capital X capital T, by a sequence of differentiations, you can check that dou u by dou x becomes x dash of t, then dou square u by dou x square will change to x double dash of t, dou u by dou t changes to capital X into t dash, and dou square u by dou t square is capital X into t double dash, where x dash is d capital X by d small x, t dash is d capital T by d small t, x double dash is d square capital X by dx square, and t double dash t by d t square. So, substitute whichever is relevant in these expressions in the given PD. For example, I have this, I have dou u by dou t equal to c square into dou square u by dou x square. So, initially my solution will be u equal to capital X into capital T. When I substitute one of these expressions, whichever is relevant in the equation, I get dou u by dou t becomes x t dash equal to c square x double dash of t. Now, what we do? Once we substitute these expressions here, we separate the variables, in the sense you try to separate the terms containing capital X and small x from the terms containing capital T and small t. That can be done immediately from this expression as x double dash by x is equal to 1 by c square into t dash by t. Is it right? Once the separation of variables happen, now you equate both sides to a common constant, say k. Once you equate both sides to a common constant k, you get x double dash by x equal to k and 1 by c square t dash by t also equal to k. So, what happens is, a partial differential equation with two independent variables is first separated. On substituting the relevant expressions, the variables are separated and equated to a constant. Now, what you can observe here is that, because capital X dash x double dash is d square x by dx square and t dash is dt by dt, these differential equations become ordinary differential equations. So, either you come across a linear differential equation whose solution is obtained by finding the complementary function, or you get a first order ordinary differential equation, as you can see here, which will be variable separable. So, solve these two, solution of these two will immediately get capital X and capital T. Once you get capital X and capital T individually, what remains is to substitute this in the assumed solution u equal to capital X into capital T, which will give you the solution to the given PDE. Now, these steps are explained in this slide. So, the method of separation of variables is applicable for solving a linear homogeneous PDE involving the derivatives with respect to two independent variables. It cannot be extended to more than two independent variables. The solution is obtained by solving two ordinary differential equations. Now, as we explained, assume the solution as u equal to capital X into capital T. You have the equivalent derivative expressions written here. Substitute these values in the given equation, separate the variables capital X, small x terms usually in the LHS, that is not a condition, and capital T, small t terms in the RHS. Then equate both sides to a common constant k, solve the resulting ODEs. I told you either, because the PDEs of order 2, either both ODEs will be order 2 or one ODE will be order 2 and the other will be order 1, and finally substitute in u equal to capital X capital T for the required solution. Some practice problems are displayed where you can try to attempt the method of separation of variables to solve these examples. So, friends, in today's session we have seen the derivation of two important partial differential equations, namely the wave equation, which is related to the vibrations of a stretched string, which is a second order PDE, and the derivation of the heat equation related to heat conduction, which is again a second order PDE. Thank you.